In the previous video, we have defined the shape operator in the case when M is a surface in space. Let's review the definition. So, if V is a tangent vector at P, then we define S of V to be the negative of the derivative of this normal vector in the direction of V, right here. This vector captures how the surface curves in the direction of V. And if we take the dot product of SV with V, that tells us how much the surface curves in the direction of V. When V is a unit vector, that will just tell us the curvature of this, the sine curvature of this curve here, the normal section here. And then remember, we define the principal curvatures to be the max and min of this inner product. So the max and min curvature of all of these normal section, right? And we saw that because this is just scalar projection, and scalar projection is the max and min when the two vectors are in the same direction. We see that these principal curvatures are just gonna be eigenvalues of this shape operator. Alright, so that's how we define the shape operator in the case when M is a surface in space. Now we want to find an alternative characterization of this shape operator so that we can generalize it to any Riemannian manifold. And we'll do so by relating the shape operator with the second fundamental form and actually find a general characterization of the second fundamental form. The key idea is that the shape operator is self-adjoint. So from linear algebra, we know that it corresponds to a bilinear form. The second fundamental form of M is just the symmetric bilinear form induced from this self-adjoint operator. In formula, it's given as follows. And this equality just comes from self-adjointness. In particular, we can think of this map here as sending every vector v to the fundamental form evaluated at v, v. In the case when v is a unit vector, this is just the curvature of the normal section in the direction of v. Okay, so what we want to do now is to give an alternative characterization of the second fundamental form that is generalizable. From that, then we can get a definition of the shape operator, because from a symmetric bilinear form we can also recover the corresponding self-adjoint operator. But before we do that, let us just address the question you're probably having in your mind. So why do we call this second fundamental form? Where is the first fundamental form? Well, the first fundamental form is the most important bilinear form on this tangent space. So what is it? Well, that's just gonna be the bilinear form given by our Riemannian metric. So historically, they call the bilinear form given by the Riemannian metric the first fundamental form. Alright, so now let's come back to the second fundamental form. Okay, so let's recall the definition of the shape operator. For every vector v, what does the shape operator send v to? Well, S of v is just going to be a minus of the rate of change of this vector field, the normal vector field, right, in the direction of v. More concretely, we can take a normal plane through P in the direction of v, right, and then we can look at this normal section gamma. Now, n composed with this gamma becomes a vector field along this curve, and we can differentiate this. And it will give us a tangent vector at P. Note that that's because this n is a unit normal, it has length 1, so by the product rule, this n dot is going to be orthogonal to n, so it lies in this tangent space at P. But let's not worry about those details for now. The important thing we want to note here is that in this definition, we needed an ambient space, because it doesn't make sense to talk about a normal vector if we didn't have an ambient space to put this surface in. So in our discussion of the shape operator and second fundamental form, we're gonna assume that our manifold is isometrically embedded into some ambient manifold, Riemannian manifold. Once we've had an ambient manifold, then now it makes sense to talk about normal vectors, because the tangent space to P of this ambient manifold is going to have this orthogonal decomposition. And so we'll just define this space to be the normal space to M at P. And every vector in this space we call a normal vector to M at P. Now, if we have a tangent vector x to this m tilde, right, at P, we will denote the tangential component by this notation and the normal component by this notation. Alright, so now let's try to rephrase the definition of the shape operator in terms of our new terminology. Let's still assume in this case that M is a surface, right, and M tilde is R3. Let's try to rephrase this shape operator. Now, if we are sloppy, we'll say that, oh, intuitively, this maps just sends every V to minus the derivative of the normal vector field along the direction of V, right, evaluated at 0. What's the problem with this? Well, this is extremely sloppy. We have to be very careful. First of all, which connection is this? Is this the connection on M tilde or the connection on M? Well, it should be the connection on M tilde because this N does not live in tangent spaces of the manifold M, right? At each point, this N is going to be a tangent vector of M tilde, not of M. So this connection is with respect to M tilde. Now the next problem is, remember, connections is with respect to vector fields, not with respect to vectors. So we have to actually assume that we can extend this vector V, right, as a vector field, big V, along the whole of M tilde. And similarly, we want to assume that we can extend this N, right, as a vector field on the whole of M tilde. Next, observe that we do not want this whole connection, we only want the proportion of it that lies in this tangent space, right? So its component that lie in the tangent space here, the tangent space. So really this map should be given by minus of this tangent component right here. And we are still only in the case of surface in R3, by the way. Alright, so we see that at every vector V, S of V is just going to be this vector, which is the negative of the tangential component of this connection. Okay, now let's try to figure out how to rephrase the definition of the second fundamental form in terms of connection. So let's say that given two vector V and W here, I can extend it to vector fields on the whole of M tilde. Right, then by definition of the second fundamental form, this should be equal to S, the inner product of SV with W, and that, by our previous discussion, is just going to be equal to the inner product of this tangential component, right, with W. And that's just going to be equal to taking the inner product of the full connection, not just the tangential component with W. Why is that? Well, because this W lie in this tangent space, and thus this normal component here of this vector is going to be orthogonal to W, so this is 0. So if we add this to this inner product, nothing change. And thus we see that this inner product must be equal to this inner product. Again, when we take the inner product of this vector with W, this vertical component, the normal component, will vanish because that's orthogonal to W. So what remains is just this tangential component. So we have that this is equal to this. Now we claim that this is just gonna be the inner product of N with this connection. So why is that? Well, observe that N and W are orthogonal, right? So this is constantly 0. This is a 0 function. So if we take V of this, differentiating in the direction of V, we should also get 0. But this is just the following by the product rule. So we see that this sum is 0, and thus we have this equality. Now, how shall we interpret this number? Well, N is a unit vector, so this is really just the scalar projection of this vector, this connection, in the direction of the normal vector N. Actually, some book defines this as the scalar second fundamental form. So I will write this as S here for scalar. So the scalar second fundamental form is the scalar projection of this vector, right, onto n, the scalar projection of this. Now the second fundamental form itself is a vector. It's this vector itself. So it's the vector projection of this onto this. And we have a notation for that. We have mentioned that it's just the normal component of this vector. Now finally, this is a definition that we can use to generalize for any Riemannian manifold. Now for any Riemannian manifold M isometrically immersed inside some ambient Riemannian manifold M tilde, we can define its second fundamental form to be a map from this the product of the tangent bundle on M with itself to the normal bundle on M, given by the following description. So the second fundamental form of V, W is just gonna be the normal component of the connection of W along V. Now in the specific case, when M is a hypersurface in some Euclidean space, then at every point P, the normal space at P is just going to be one-dimensional. So we can have we can choose a continuous unit normal vector field on M. And in that case, the second fundamental form always give a multiple, right, a scalar multiple of the unit normal. Now this scalar is called the scalar second fundamental form in that case. It's given by taking the dot product of the second fundamental form with the unit normal. Now on each tangent space, this second fundamental form is going to give a bilinear form. And we can then define the shape operator to be the self-adjoint operator that induces this bilinear form. Now because the shape operator is self-adjoint, it's gonna have real eigenvalue. This is because of linear algebra. And we call this the principal curvature. And again, we define the Gaussian curvature to just be their product, the product of the principal curvature. And we can show that the Gaussian curvature is actually intrinsic by expressing it in terms of the curvature tensor.